In 7.3, we're going to be talking about E. Your book calls this section Use Functions Involving E, but really it's more about E than it is the functions. You've probably never seen it before, so first we're going to talk about what E is, then we're going to talk about why we use it, then we're going to talk about how to use it, which will take the bulk of the lesson. We're going to simplify expressions that have E's in them. We're going to evaluate them using a calculator. I'll show you how to do that on the graphing calculator. And we're going to graph some by hand, functions that have E in them. Exponential functions, specifically. Which brings me back to what is E. E is a number. It's like pi. It's irrational. So it has a decimal. The decimal never forms a repeating pattern, and it never stops. I kept writing it until I ran out of room. It keeps going forever. This is E. It's around 2.7, so if you remember that it's 2.7, that can make graphing a whole lot easier. It might also help you to note that E squared is around 7.4, because sometimes you want to graph that as well. Why is E? Turns out when you study exponential growth in real-life situations where things are constantly changing, E kind of pops out from the math. At this point, I don't think I want to get more specific about how it pops out, but as you start moving from, in 7.1 we talked about compound interest, and as you start moving from things that compound like yearly or monthly toward things that are compounding all the time, for large populations, for example, they're constantly growing. Temperature change, it's not like you put something in the fridge and it stays at its temperature for 3 minutes and then all of a sudden drops down. It's constantly changing temperature. So you end up with math, and if you study the math, this number just kind of pops out. A lot like when you study circles and pi kind of pops out when you start doing math with it. So why is E exponential growth? Which is why we're learning about it now in our exponential growth section. How is E? Really, when you see E in a situation, you're going to treat it pretty much like you would a variable. Technically, it's not a variable, it's called a constant because it has one value and doesn't change. But all of the rules we use for variables also going to apply to E. For example, if you have two powers with E as a base and you're multiplying them together, you can, just like you would if those were, say, x's, you can add the exponents together. This is the same as E to the 15th power. 9 plus 6 is 15. Similarly, if you are dividing 60e to the 8th divided by 12e to the 3rd, treat it just like you would if E were a variable. 60 divided by 12 is 5. E to the 8th divided by e to the 3rd. When you're dividing powers with the same base, you're going to subtract the exponents. 8 minus 3 is 5. So this becomes 5e to the 5th power. We're not going to worry about what E is. We're just going to treat it like a variable. As far as evaluating these expressions to get actual decimal approximations, that's really something you're going to use your calculator for. You could try them by hand with an approximation using some of these decimals, but why bother? E to the 15th, for example. Now there's actually two E buttons on a Texas Instruments graphing calculator. There's this one here that's just regular little E, and there's this one over here that's designed for if you're going to raise E to a power. You're probably going to want to use this one most of the time. It's above the LN button. We're going to use this most of the time because usually when we're using E, we're raising it to a power. But if you just wanted E, you would push the blue button there, the shift button, and then push this right here, divide, and it'll give you just regular old E, 2.71. If you need it to a power, this one's a little bit faster, so you don't have to make the power yourself. E to the 15th is what we're doing right now. E to the 15th is very big. 3,269,000. 3,269,000, 17.372. It keeps going, but at some point you're going to need to stop writing digits. 5e to the 5th, very similar. 5, put in the e to the 5th, 742-ish. I suppose in algebra we like 2 decimal places by default, so there it is. So that's simplifying and evaluating. The last thing we're going to do is graph. Now in this case you are going to need almost certainly to plot decimal points in your graph. Don't let it intimidate you. If you remember what E is, and especially if you remember what E squared is, these aren't so bad, but you can always use your calculator to find a particular decimal so you can plot it. Let's start with this one, y equals 4e to the 0.5x power. Now the first thing I do anytime I'm graphing an exponential function is think about my horizontal asymptote. Since there's nothing being added outside, there's no k out here, the horizontal asymptote is at 0, y equals 0. So it's going to come up from the x-axis, and then it's going to bump into the air really quick, because that's how our exponential functions work. Now I just need to plot a couple of points. So let me make an xy chart. Nice and easy. The easiest point is always going to be where the exponent is 0. In this case, to make it 0, I'm actually going to stick in 0. 1/2 times 0 is 0. E to the 0 is 1, because anything to the 0 is always 1. So this point is 0, 4. Now I'd really like this to be 1, and 1/2 times 2 is what makes 1. So that gives me actually 4 times E, which I could probably approximate by hand, but why bother? I have a calculator. 10.8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.8. That is way up there. But that gives me my 2 points. I'm going to go above and beyond and also stick in -2, which will give me 4e to the -1 power, or 4 divided by e, which is 1.5. So -2, 1.57, well, 1.47, 1.5. So here's my, turn my graph. I draw them much nicer this way. I'm going to come down through my points toward my asymptote, and there's my graph. In case you were wondering, this is a growth function because our base e is bigger than 1. E is around 2.7. It's definitely bigger than 1. And we learned in 7.2 that when the base is bigger than 1, you're going to get a growth function, and when the base is less than 1, you're going to get a decay function. It turns out there is an exception to this rule that we are going to talk about right now, and that's if there's a negative sign in the exponent. So I'm going to graph e to the -2x. In this case, I still have, let me put something out here, +2, just for kicks. So in this case, I have a 2 being added on the outside, which raises my graph 2 spaces and moves the horizontal asymptote up here to y equals 2. Now the other thing that happens is there's a negative in my exponent, and I keep trying to remind you, and people keep staring at me blankly when I ask, a negative in an exponent turns it upside down. It turns it into a division problem instead of a multiplication problem. So this is actually the same as if I had 1 over e to the 2x power. Now, 1 over e is less than 1. In fact, anytime you have a number bigger than 1 and you take its reciprocal, you will always get a number less than 1. 1 over e is 0.36. It's 1 divided by 2.7. So having that negative in there, we don't need to write it this way. We can leave it this way. But when we're trying to decide whether it's growth or decay, when you look at e and it's bigger than 1, if there's a negative in front of the variable in the exponent, that's going to flip the graph around. So this one, even though e is bigger than 1, is actually going to be a decay function. So if you've got e and there's a negative in front of the x there, it's going to be a decay function instead of growth. And that'll be true even if it's not e. If this were a 4, it would still be decay. If this were a 1/3, which is less than 1, the negative would flip it around and it would become growth. Now that I have my asymptote and I know it's going to be growth or decay, I'm going to find a couple of points. Again, the easiest point is always where the exponent is 0. So if I stick in 0, I get e to the 0, which is 1, plus 2 makes 3. Now in this case, I'm probably going to need a calculator either way, but I'd really like this to be e, because I know e is 2.7. So I'd really like this to be 1. And what do you multiply by negative 2 to get 1? Well, negative 1/2. So negative 1/2 times negative 2 is positive 1. That'll give me 2.7 plus 2 is 4.7. So negative 1/2 is about 4.7. 1, 2, 3, 4.7, right there. So I'm going to come from my asymptote. I'm going to go through my points. There's my graph. I got one more graph. It's, of course, the most complicated. Y equals e to the negative 1.5 times x plus 2 minus 4. What a mess. So when I graph this one, the horizontal asymptote has been moved down 4 spaces. So it's going to be down here at y equals negative 4 because of this negative 4 out here. The other thing that's going to be different about this one is because of this plus 2, in order to make this 0, I'm not going to stick in 0, I'm going to stick in negative 2. Because negative 2 plus 2 is 0, multiplied by negative 1.5 I get 0. E to the 0 is 1. 1 minus 4 is negative 3. So negative 2, negative 3 is right there. Looking for a minute just because I'm curious. I have e as my base, which suggests growth, but a negative in my exponent. This one's also going to be decay. I want to stick in something that's going to be nice. I'd like to make this 1. 2/3. No, I'm going to use my calculator. So I'm going to stick in 0 and hope that it's not too big. So when I stick in 0, I'll get 2 times negative 1.5, which would give me e to the negative 3 minus 4. Oh, that's going to be small. Right. It's the other way to get big. So e to the negative 3rd power is 0.497-ish. Then when I subtract 4, negative 3.95. So that's going to be really close to negative 4. Not really surprising. It's a decay function. It's going to be right close to the asymptote. I'm not really comfortable drawing this curve yet, so I'm going to stick in negative 4 as well. I'm sorry if you feel like that's a waste of time. I like my graphs to look nice. So if I stick in negative 4, this is negative 2. Negative 2, that's e to the 3rd power. Oh, I think this is going to be too big. E to the 3rd power minus 4 is 16. I should have stuck in negative 3. So I will do that now, although that's going to give me e to the negative 1.5 times negative 1, which is 1.5 minus 4. 0.48, which is much easier to graph. Now I'm much more comfortable drawing my curve. There it is. In case you've forgotten from earlier, the questions in your book will frequently ask you for the domain and range. It's relatively new for you guys. But the domain for an exponential function, since it always goes all the way to the left and all the way to the right, the domain is all real numbers every time. The range is going to be the y's involved. Find your horizontal asymptote. In this case, it's 0. And here the y's are all greater than 0. This one here, domain, all real numbers. The range, my lowest, well, it's not quite as low as 2, but all my y's are going to be bigger than 2. That's my horizontal asymptote. This one, domain again, all real numbers. And my range, since my horizontal asymptote is at -4, all of my y's are bigger than -4. So this should be enough to get you started. Let me know if you have any questions.